about 23,000 acres per year. With scenario 2, it's now additive. We're now have treatments planned for the WUI threat zone, which is a little bit farther out and from developed areas, up to 1.25 miles out from. And with scenario 3, it's now scenario 2 plus areas in the general forest, which are areas that aren't otherwise, so areas under Forest Service control that are otherwise not in WUI or in another classification like roadless or wilderness. And so as we add more scenarios, we are increasing the amount of area treated per year. And then with the differences between scenarios 5 and 6, even though the targeted area is the same, one features more prescribed fire, the other more mechanical thinning. And so the framework that we use to project these disturbances and forest conditions moving forward is a model called Landis 2. It was developed in part by Rob Scheller at North Carolina State University. And it is a landscape level model. Its frame of reference is tens of thousands to hundreds of thousands to millions of acres. To handle the computational load, trees are grouped into species age cohorts based on presence within a cell. And it tracks carbon as well as other nutrients across different pools for those different cohorts. So it'll track live, dead, above and below ground carbon. As I said before, it incorporates human and natural disturbances. The figure on the right shows how these spatial processes play out and that these processes can affect each other. So areas that might burn under a prescribed fire may slow down natural ignitions of wildfires. And this is done in a raster format across this 2.4 million acre landscape. Additionally, it incorporates climate change projections going forward, which have direct and indirect effects across the landscape. But climate change, in this case, will impact forest succession. Species have different optimal temperature and precipitation combinations. Climate change also affects fire, the rate of spread of fire across the landscape and severity, as well as acts as a trigger for insect outbreaks. And I will talk about fire and insects in a little bit. So what do these future climate projections look like? Well, one of the things that we did was, given that there are over 30 different climate change projections under the most recent round of modeling, we relied on the CalAdapt fourth climate change assessment to kind of winnow down these different projections to ones that really covered the gamut in terms of combinations of hotter, drier, wetter, warmer. And to give you a sense of how these played out, we chose the 4 that they recommended most. If we couldn't run all the different climate projections, we chose the 4 that covered the most ground. So how those played out, Hadjim was the warmest and driest, and the figure shows the difference between a sort of decadal average in terms of change in precipitation and temperature between 2050 and reference conditions and our contemporary climate, and then the 2090 to 2100. And so for this landscape, what we see is that without a doubt, this landscape will get hotter, about 30% hotter by the end of this century. But we see also a wide range in potential precipitation conditions, some with little change from present day conditions to an increase of almost about 50% over the last 2 decades. So these sorts of climate projections have a big impact on the sort of things like the potential future fire weather. So I recognize that this graph is pretty messy, it's pretty noisy. This is the daily calculated fire weather index across this particular landscape. And for the Land is 2 model, fire is a function of the fire weather index. And what I really wanted to highlight is that under present day contemporary climate conditions, we see a huge variation every couple of years in the severity of the fire weather index. And this red box that I'm trying to highlight is 2019 and part of the 2020 values. And I just threw a horizontal line across showing that most recently, conditions in 2019 and early 2020 are more extreme in terms of fire weather than any of the future climate projections going forward up until about the year 2095. So first off, that kind of points to sort of a cognitive dissonance between what we are currently experiencing in California and what these future climate projections are showing. If we kind of strip out the noise and just focus on the annual maximum, well, we're still seeing current conditions with more extreme future or fire weather than what's being projected into the future. On another side of the climate issue is future climatic water deficit. And climatic water deficit is the amount of water trees would use if they had access to it. More formal definition is the difference between potential evapotranspiration and actual evapotranspiration. And so it tracks the amount of deficit of what the plant needs in terms of water. And for the Land is 2 model, insects are a function of climatic water deficit. And to go back to try and associate or correlate previous insect outbreaks with climatic water deficit, we use different data sets as well as expert opinion from entomologists into correlating those different things. But what the future holds in terms of the sort of projected climatic water deficit is that even though we experienced that big drought in the realm of 2012 to 2017, ultimately that pales in comparison to the sort of deficits that we will be facing in the future. And so the potential severity of drought conditions into the future is only going to increase from present day conditions. So how does this play out in terms of the results, comparing those different management scenarios, and how do they do in terms of managing for things like high severity fire or insect outbreaks? And associating or kind of collapsing the different management scenarios into the different climate pathways, what we see is that there is a pretty big outcome resulting from the different climate change projections going into the future. But when we spread out and average across the different climate projections for the different management scenarios, we also see that management is driving some differences in the amount of area burned at high severity fire. And when it comes to insect outbreaks, for this area, averaging across the different the management scenarios on the left to just try and isolate the climate signal. What we see is that climate really drives the insects, which is, of course, one of the assumptions built into the model. So that result is not surprising. But what happens when we consider the management scenarios, averaging across the different climate change projections to isolate the management signal? Well, what happens is that management doesn't really make that strong of impact on the amount of area experiencing mortality due to insects. And that is a bit surprising, but also not really, given that insects don't really respond necessarily to individualized small acreage treatments. They have dispersal rates that far exceed what a sort of standard several hundred acre thinning project might provide. And so it gives a hint that maybe we do need to think even beyond the treatment rate within scenario 6 or 5 in terms of the number of acres treated per year. Because again, right off the bat, within the first 20 or so years, we are seeing large insect outbreaks. So of course, between fire and insects, what we're going to see in terms of forest composition is going to radically shift, and it's going to shift pretty quickly. So the insects that we simulated target mainly pine species. Western pine beetle, of course, targets ponderosa pine, Jeffrey pine beetle, Jeffrey pine, so on and so forth. But with the selective pressure against pines, what we see is actually that Douglas fir starts to take over. They become much more prevalent, and stands that were originally mixed conifer are now becoming a lot more Doug fir dominated. What we also see is selective pressure, more so due to climate change for these high elevation species, red fir, white, mainly red fir, but some of the other high elevation pine species. And so what were these high elevation patches that include red fir or white bark pine, western white pine, in those higher elevation areas? Well, climate change is going to make it difficult for those species to continue on into the future in the abundance that they are now. So this graph is simply just a distillation of the change through time of the maps above. And again, the highlight that I'm trying to, or the point that I'm trying to highlight is that what originally was a sort of mixed conifer is going to decline in terms of area, and it's going to be replaced by more of a pure Doug fir stand. So just to summarize, the sort of management scenarios that we sketched out does impact high severity fire, or the amount of high severity fire, but it doesn't matter too much for the amount of area impacted by insect mortality. Forest composition is going to change substantially and at a pretty rapid pace. And more or less, given these projected future climate conditions that we used for this study, insects are going to shape these forests in the Central Sierras more than fire will. And I realize that that is very much a different story than what is currently going on at present. But, you know, that really only highlights the need for actions now. Because even if we do take a rosier picture of what climate change might bring. If it's not fire, it's going to be insects that really do damage to these forests. And that's all I have. So if you have questions, feel free to email me. Thank you.